Okay, physics students. So in this video, I'm going to introduce you to the main concepts of projectile motion, and I just want to tell you up front that this is one of those cases where the reality of how we deal with projectile motion is a bit counterintuitive. But in this case, the fact that it's counterintuitive actually makes it a lot easier for us to deal with analytically. And of course, like any other topics in physics, we make certain simplifying assumptions, which turns out in this case, the main simplifying assumption is that we neglect air resistance, which is actually in reality, a very big factor. But we generally don't consider air resistance when we use the equations of motion to deal with projectile motion problems. So let's go ahead and get started, okay? I just want to show you guys something really cool to start off. I think we did this, I showed you this in class, okay? This picture shows two steel balls falling through the air near the surface of the Earth. They're both released at exactly the same time, okay? But the big difference is that one of them goes vertically downwards. It's just allowed to fall straight down, and the other one has an initially a horizontal velocity and no vertical velocity, okay? Well, of course, this one doesn't have a vertical velocity either to start off with, but this one, the point is that the ball on the right is projected horizontally initially. And what you notice here is that, well, this is strobe photography. So the camera takes a picture at consistent time intervals, okay, and the same time interval, let's say it's, I don't know, it might be 1/100th of a second or whatever, okay? So the thing to notice, keeping that in mind, is that the ball is at the same vertical position. If you draw a straight line from the left one to the right one, you'll notice that they're in the same vertical position, okay, at every single time interval, which is really somewhat counterintuitive. You see that? You see how they line up horizontally? Okay, so to me, that's somewhat counterintuitive. Most people would think that the ball that's shot off horizontally would fall more slowly towards the center of the Earth, but apparently that's not the case, okay? Now, just talking about the vertical, you know that gravity acts only in the vertical, okay? So what's cool about this is that we can actually treat the projectile, or the steel ball that's being shot off to the side, we can actually treat that as if it's a ball falling straight down towards the center of the Earth. And in that case, we can use this very simple equation of motion right here, which of course you should recognize as really just equation 1 in our kinematics equations, V equals U plus AT. Okay, doctored up just a little bit. I have here A sub y and V sub y, just to remind you that you're only dealing with the vertical motion of that. And there's only acceleration in the vertical, remember, okay? All right, now the other thing that's really interesting is if you draw a bunch of vertical lines corresponding to the position of the ball at certain time intervals, the one on the right, okay? Here I've drawn a yellow line to line up with exactly the leading edge or the right edge of the steel ball. You notice something, and to me this is even more counterintuitive originally. You notice that that the horizontal velocity remains constant. And I know this because if we assume, rightfully so, that the time interval between photographs here is constant, and if the spacing between the balls, or the horizontal displacement is constant, which it appears to be, then that can only lead to one conclusion, and that is the horizontal velocity is constant. Okay, so in this case, we use this, which is so simple, it's not even an equation of motion. This is just distance over time. Okay, all right. That's all we do in the horizontal. It's actually very, very easy, okay? And I want to point out one thing right now. This, the horizontal distance or displacement that a projectile covers, we use this term range in physics. It's called the range. So for example, in this case, I have the change in displacement in the horizontal delta S sub x between this interval and this interval, okay? Well, that's the range, that's the horizontal distance the ball traveled in that particular time frame, okay? So I want you to note, most importantly, how the vertical displacement is the same for both, but the horizontal distance is constant between each frame. And what this really means is that the x and y components of the velocity are actually completely independent of one another. Okay, so we treat them totally differently, and I'll show you some examples of how we do this in a little bit. Okay, all right. Now we're going to consider an object not just tossed sideways, but an object tossed upwards and horizontally, like this tennis ball. Okay, so it might start over here, and it might go like this and go to the right. Okay, well, it looks like actually the way that it's measured, since 0 is over here, someone threw it from this side. It looks like they airbrushed out their hand or something. Anyway, here's the ball. Okay, in my treatment of this the path of the tennis ball, what I'm going to do is I'm going to treat it as if it's starting from the left and going to the right, just so you know. Okay, all right. Now, because gravity acts only in the vertical, I can actually draw for each frame here. I can draw an acceleration vector. Okay, which I'm calling G. All these red vectors are acceleration vectors for the tennis ball. So what's interesting, if you remember from last time, that even when a ball is going upwards, it's in free fall, and the acceleration of gravity is acting to slow it down, okay? And at the very top of its trajectory, the velocity, of course, is 0. Then it starts to speed up again as it comes back down because of this vector G, this acceleration vector that's pulling it down, okay? So remember, Vy acts on an object in free fall in the vertical. Now we know that Vx remains constant, okay? And I want you to notice that the vertical displacement is symmetrical up and down, and the horizontal distance is constant between each time frame. What I mean by symmetrical up and down is I'm saying, okay, if this ball right here, the position of this ball right here indicates the very top of its trajectory, if you draw a horizontal line between each of the balls on either side, you notice that they're more or less in the same vertical position on either side. Notice how this one is a little bit above this one, okay? And that actually proves that in this real drawing, the ball was thrown from left to right, okay? And I'll talk about that a little bit in just a little bit. And I want you to note here that that the change in displacement for each time interval, I have S sub x is 0.55 meters. You might want to pause the video and just see if you agree with that according to that scale. Now, if we knew the interval between the time frames, we could actually determine exactly what V sub x is, okay? And I'm going to do that right now, okay? So I'm going to figure out exactly the time between the time frames as much as I can, and the horizontal velocity V sub x of the tennis ball. What you should do is pause the video right now and try this problem on your own before you see my solution. Okay, all right. So again, I'm noting I'm only going to deal with the left-hand side of this diagram. Okay, remember the position of the ball right here. I'm assuming that that's t equals 0, and all these are at later times. This is the latest time over here. So it's going from upwards from left to right, as seen in the diagram. Okay, and I'm drawing acceleration vectors only for the first half of its path, just because I don't want to make this diagram really messy and complicated. Okay. Now the first thing I'm going to do is I'm going to actually measure according to the scale. I'm going to measure the displacement during each of these intervals 1, 2, 3, 4, 5, 6. Okay, and these are the values I got. You might want to pause the video and verify that. Okay, these are ballpark estimates, obviously, because my instrument is not super precise, but it's precise enough. Okay, and I'm extending these horizontal yellow lines over to the right-hand side to the part where the ball is actually going down. And one thing that you notice here is that, remember, I mentioned before, the ball is actually lagging on this side. For example, I'm showing this, the yellow lines on the left-hand side correspond to the top of the ball. You see how on the right-hand side, the ball is lagging? The top of the ball is now here, and now it's here, and now it's here. That's because in reality we can't really neglect air resistance, okay? So air resistance, because there's a drag force pushing up on that ball, it's actually causing it to not fall quite as far as it would theoretically, okay? All right, so that's the effect of air resistance, everything on this right-hand side, okay? All right, now I'm going to consider interval number 7, which is between the very top and this ball right here, okay? I'm going to consider a big interval, S7, and I'm using the second equation of motion, and I solve for t using this distance right here, and I'm saying it's negative 0.395 meters according to my scale here, and I get 0.28 seconds, okay? 0.28 seconds between the top of its trajectory and this spot right here, okay? Now, because that encompasses 6 time frames, okay, I'm going to divide that total time by the number of time frames, and I get 0.0, the actual velocity, the horizontal velocity of the tennis ball. What I need to do is I need to divide the distance it travels between each frame by the time between each frame. So I get 0.055 meters as before in the previous slide, divided by 0.047 seconds. And I get that the horizontal velocity, the horizontal speed, is 0.117 meters per second, okay? So I just want to point out that this is very approximate, and the reason is because you see how the ball lags when it's falling, okay? By the same reasoning, the ball is also lagging when it's going up, correct? Because it's got air resistance going up, okay, as it does going down. So, but this is the best that we can do, really. I just want to point out, again, how important it is, this fact that we neglect air resistance. Air resistance is really, really, really important, and it's a huge simplifying assumption that we make, okay? So let's do a couple of examples, all right? Try this one on your own before you see my solution. Okay, so a ball is kicked horizontally off a 50-meter high cliff at a velocity of 10 meters per second as shown, and I'm asking you to find the time of flight of the ball, or the time it takes for the ball to hit the ground, the range of the ball, the horizontal distance before it hits the ground, and the velocity of the ball at impact. And for part C, I'm asking for a magnitude and a direction. Okay, so let's go ahead and get started on this one. All right, so the purple dashed line shows the path that the ball takes as it goes from the cliff to the bottom, and the green vector here shows the initial velocity vector. The red vector shows you the final velocity vector. And in keeping with IB protocol, I'm going to call the initial velocity, I'm going to call it U, and I'm going to call the final velocity V. And I want to point out that this drawing is not to scale. Okay, all right. So because the ball is initially shot horizontally, the initial velocity vector is just u sub x, which is 10 meters per second. U sub y is 0, and theta is 0. There's no angle to it. Okay. Now I've already broken up my final velocity into x and y components, and I'm calling this angle to be beta. So I have it all set up for me to solve, especially part C of the problem. Okay. Now the time of flight of the ball, it's very simple. Remember, I just treat the ball as if it's falling vertically, okay? And because time doesn't have x and y components, obviously, it'd be really weird if it did, okay? I don't have to deal with time as a vector, okay? The time in the vertical is the same as the time in the horizontal, okay? So considering only the vertical, here's my Suvat table. I solve for t, and I get 3.19 seconds for that ball to fall from rest, okay? All right, the range of the ball is now very easy. Once I know the time, I solve for s sub x. I know that v sub x is 10 meters per second. I get 31.9 meters, and that's this distance right here. That's 31.9 meters, okay? All right, now the velocity of the ball is a little more complicated, but it's nothing that you guys can't handle because you've studied vectors like crazy, and you're very good with vectors, okay? V is shown, v sub x is 10 meters per second is given. So I already have v sub x as 10 meters per second because that's what was given to me originally. In reality, it's a little bit less than that, but our simplifying assumption is that v sub x does not change. Okay. Now, to find vy, I go back and I make another Suvat table, and this time I have the time from part A, which is 3.19. Okay, again, you can probably solve it however you want, a couple of different ways. I get 32.9 meters per second for v when I use the Pythagorean theorem and the first motion, or the first kinematics equation here. Okay, and then I find that beta is 72.3. So if you're not getting my reasoning, especially for part C, make sure that you pause the video and go back and rework it. Okay, because the next example I'm going to do for you is a little bit more complicated. Okay, and it's complicated because of this. Now I have the same ball. I'm kicking it off a 50-meter cliff. Okay, the velocity is 10 meters per second, but now it's up at an angle of 30 degrees. So I have u equals 10 meters per second again. Theta, as shown in this diagram, is 30 degrees. I have my u sub y, my u sub x. Now the path, the purple path, follows this dashed line. Okay, I've got it all set up for you again to find v at the end of its journey when it hits the ground. This drawing is really not to scale, okay? You don't have to worry so much about scale drawings as long as you have a drawing that kind of shows you what's going on generally physically. Okay, so again, the time of flight of the ball. I'm only going to consider the vertical motion of the ball, but it's more complicated now because what I have to do is I have to calculate the amount of time it takes for the ball to get up to the top of its trajectory. Okay, that's going to be basically one problem. And then from there, I have to find the amount of time for the ball to get from the very top all the way down to where it started plus 50 meters farther. if that makes sense. And in the second part, where you're considering it dropping from the top of its trajectory, your initial velocity is, of course, 0, because it's as if you're dropping it from rest at this point right here, if that makes sense. Okay? All right? So, and of course, the total time would be the time taken to get to this point plus the time taken to get all the way to this point. Obviously, the second part is going to be a greater time than the first part, right? Okay, let's see. So for the time up, notice how I have my subscript y's for all my variables. Okay, I find that the time to get up is about a half a second from here to here. Okay, the time down, again, as measured from the top of the path, okay, is again a little more complicated, because now I have to find the maximum height above the starting point, and that plus 50 will be the total distance that the object covers when it hits the ground. Okay, and I got that the highest it gets is 1.27 meters above where it started. Okay, so that means that its total distance as falling from here is 51.27 meters, because I'm adding 1.27 plus 50. Okay, now here's my new SUVAT table. Again, notice the subscript y on all the appropriate variables. I don't have one on t because there's no difference between the y and x component of time. There's no such thing. Okay, and I get that the time is 3.23 seconds. I add that to the 0.510 seconds I got before, and I got 3.74 seconds for the total time taken for the ball to hit the ground. Okay? All right, and we're going to continue this problem. Okay? I want you to find the range of the ball. Well, this is the easiest part of this entire problem. Okay? You find that u sub x, okay, using simple trigonometry, is 8.66 meters per second. Okay? And I'll let you figure that one out. That's the cosine, deals with the cosine of 30 degrees, the cosine of that angle. And I got that delta S sub x is equal to 32.4 using the 3.74 seconds that I computed in the previous slide. Okay? The velocity of the ball at impact, okay? Well, you know that the initial horizontal velocity equals the final horizontal velocity, so we already know v sub x, which is 8.66 meters per second. Okay. Now, in the vertical, we treat as a ball dropping from rest at a height of 51.27 meters, which was the high point here. How fast is it going to be going? It's clearly going to be going faster than the vertical component of it at this point, because it has 50 more meters in which to speed up. Okay. So here's my SUVAT table. I've got 51.27 meters there. Okay. And I'm using the first equation of motion to find its 31.7 meters per second. Okay, but that's v sub y. That's the vertical component of the velocity. Using Pythagoras and the inverse tangent function, I get 32.9 meters per second for this velocity right here, and 74.7 for beta. Okay, and the maximum height of the ball, well, we already did that one. It depends on how you define it. If you define it as the height above where it started, it's 1.27 meters. If it's the height above the ground, which is usually what how you would interpret that, it's 51.27